Okay, people, let's get into this next learning goal. Number 5, understand how the thermodynamic potentials are connected to equilibrium. And this is, of course, related to your Igor 4 assignment. So this should give you some nice support understanding that assignment. So we've developed these two equations previously where we can see when the delta G for the whole process, so the reaction and mixing equals 0, then we're at equilibrium. So then now, noting that we can write delta G as delta H minus, so let me try that again, minus T delta S, we can plug that into this expression for the equilibrium constant and arrive at the following. So K equals E, and I'm going to write this as a double exponential. So that's going to be exp of, it'll be negative delta H of reaction divided by RT. And then now plugging that in and doing some algebra, we'll have the exponential of, so now the negative and the negative cancel, and the T cancel. So that becomes delta S Rxn divided by R. And so this is our double exponential, if you will, here. And if I take the natural log of both sides, I get natural log of K equals negative delta H of reaction divided by RT plus delta S. Let's make sure that I'm being consistent and writing Rxn there. Rxn divided by R. And so now if we were to make a graph of, in this case, it'll be 1 over T versus natural log of K. We can see the natural log of K is Y. And then my slope becomes delta H divided by R. My X is 1 over T. And then now delta S over R becomes the Y-intercept. So if we have an endothermic reaction where delta H is greater than 0, you can see that that will correspond to a negative slope, right? So that's a delta H greater than 0. So that's endothermic will result in a negative slope on this graph. And if we have a delta H less than 0, that's an exothermic reaction. And we can see that there's a negative sign in the equation. So if we had an exothermic reaction, it would look something like this, okay? So those aren't describing the same reaction. That's describing like two different reactions and what it would look like if we had an exothermic versus endothermic. Okay, so just as a reminder here, when we think about how these potentials are connected, when K is greater than 1, we recognize that products are favored, right? When K is less than 1, reactants are favored. So now, noting this expression and how it goes, when we have an endothermic reaction where the delta H is positive, we still have a negative sign there, right? So e to a negative quantity is going to be less than 1. So this indicates that endothermic reactions have a tendency to favor reactants. But now if we think about this in an exothermic reaction means delta H is negative. So a negative makes that a positive. And when we have the exponential of a positive quantity, it's greater than 1. So that means exothermic reactions tend to favor products. And that kind of makes good sense when we think about it, right? When we have an endothermic reaction, we need that extra push to move it on to products. And if we don't have that extra push, then reactants will be favored. Now, what about the case with delta S? So let's draw up that same equation again and talk about it with this figure that I've got here. So, and I'm just going to write that as delta H over RT and exponential of delta S over R. Okay, so let's consider two scenarios here. So both of these scenarios are endothermic reactions. In this first one, in A, we can see the Boltzmann distribution of A. And so let's make sure we're also noting that this is A in equilibrium with B. So this is our very simple equilibrium example. So here are the energy levels of A, and here are the energy levels of B. So what you're supposed to gather here is the delta S for this process going from A to B is small. And the reason why we can say that is because the energy levels for A are packed tightly together. The energy levels for B are packed tightly together. So now, because this is a small entropy change, this endothermic reaction still favors reactants. And it favors reactants because now, once again, we remember that an endothermic reaction already favors reactants. But now when we consider what this other exponential is doing, if the change in delta S is small, it makes this quantity less important. So the delta H then dominates. But now if we look at this expression here, we can see delta S is large. And we can recognize that it's large because A has a very small number of microstates with the way that these levels exist here. So the levels aren't packed as tightly together. But you can see B still has a large number of states packed tightly close together. So there is a big change in the number of microstates going from A to B. So that's how we can conclude delta S is large here. And because delta S is large, that means this chunk of the equation will win. So this would favor products, right? So it's not necessarily universal that endothermic reactions only favor reactants. If there is a large enough change in entropy from reactants to products, then an endothermic reaction can definitely favor products. And of course, we have to play the same game with the exothermic reaction. That being said, exothermic reactions already favor reactants to begin with. But as we might guess, then the opposite becomes true with an exothermic reaction. Okay, folks, that's all I wanted to say about our connection of the thermodynamic potentials to the equilibrium constant. I'll see you in the next video.